Hello, my name is Jamie Tayar, and I'm a third-year graduate student here at The Ohio State University. I'm going to talk to you today about my recent paper entitled Rapid Rotation of Low-Mass Red Giants Using APOKASC, a measure of interaction rates on the post-main sequence. Almost half of stars form in binary systems, and it is well known that such stars can interact to form interesting classes of objects. What is less well known, however, is exactly when and how often such systems interact. In this paper, we identify stars that have likely interacted or merged with a companion by measuring their rotation rates. In general, we know from stellar evolution models how fast stars should spin on the giant branch. Low-mass stars slow down on the main sequence due to angular momentum loss from magnetized winds. As their envelopes expand on the giant branch, they slow down even more, to rotation velocity substantially less than 1 kilometer per second. In contrast, higher mass stars do not lose angular momentum on the main sequence. We therefore expect that they might continue rotating rapidly, at least on the lower giant branch, before angular momentum conservation slows them down. To compare actual stars to these theoretical predictions, we use the dataset available in the Apogee Kepler catalog. These stars have measured masses, radii, and surface gravities from astroseismology done on Kepler light curves, as well as metallicities, effective temperatures, and compositions from the Apogee spectroscopic survey. In this paper, we add to this dataset a measurement of the surface rotation velocity of each star by measuring the width of its spectral lines. Out of our sample of almost 2,000 giants, we identified 10 stars rotating rapidly, 71 stars with moderate rotation, and 15 giants rotating anomalously, where anomalously is defined as moderate rotators spinning substantially faster than any other star of similar mass, surface gravity, and metallicity. While some of our moderate rotators could be more massive stars evolving normally, we expect that all of our rapid and anomalous rotators result from some sort of interaction. Additionally, we note that these rapid and anomalous stars are more likely to be lower metallicity and clump giants, which is consistent with our current expectations of binary populations and binary evolution. Because the stars in our sample are so well studied, we attempt to identify the cause of the rapid or anomalous rotation where possible. 3 such stars, for example, are located in eclipsing binaries, and at least 2 are likely rotating rapidly because of tidal interactions. 1 star has a second pulsation signal in its Kepler pixel from a red giant which may or may not be physically associated with a rapidly rotating star. We also identify 1 star that, like blue stragglers, is clearly more massive and less evolved than stars of similar metallicity. We hypothesize that this star is the result of a stellar merger. One final plausible explanation for the rapid or anomalous rotation of our stars is the accretion of material from a substellar companion. While we don't have optical spectra to check for the enhanced lithium abundance expected in such stars, we do check that the carbon isotope ratios in our likely interaction products are not consistent with any sort of extra mixing which would confuse such identification. In addition to looking at these specific stars, we also examine the full rotation distribution. We notice, for example, that we have fewer rapid rotators than field surveys led us to expect, something we suspect could be due to the suppression of pulsations in rapid rotators or close binaries. Additionally, the identification of moderate or rapid rotation in low-mass clump stars suggests that at least 7% of low-mass stars are spun up by a companion on the upper red giant branch. Finally, we note that we do not see the large fraction of intermediate mass stars we expected to have measurable rotation rates. This could have interesting implications for our understanding of angular momentum loss and transport in such stars. If you're interested in the details of our method and analysis, check out our paper, which was posted on the archive today.